pretty self-explanatory.
Yeah.
And then the y-intercepts, you just plug in what you got for your x-intercept and solve.
Yeah. Pretty much.
Easy. The crit points, you use the first derivative
To
find and solve it for 0. Set it equal to 0.
Yeah, setting equal to
Derivative
0.
chart. Remind me on the first derivative chart. And like the second derivative chart. 2 points that your points that you find in your crit points. Your zeros, right?
In your derivative, yeah, that's right.
And then you find a number in between. So like on this one, you have a crit point at -5 and 1.
Right.
So then you would find a point on the outside of -5, like a -6 or a -7 or -8, something that's lower.
Okay.
Like 1 and -5.
Okay.
So between a 0. And then something above 2 or something above 1, which would be 2. Right?
Mm-hmm.
So then what? Do you plug those numbers in to the equation or into the derivative and solve it and see if it equals a positive number or a negative number? To get see like on the first derivative chart how it has like a plus and a minus and a plus?
Yeah, I'm following. It has to do with it. If it's positive, it's negative, or so I remember. It's like they said if it's like above or below the graph. Isn't that right? Did you watch the first video yet?
The what?
The video for Monday?
No.
Okay, well they talk about how if it's above or below the graph. Let me see if I can pull it up real quick. I have it here with me. Or
And
do I?
I get that like when you plug in -6 into when you plug in like -6 or -7 into the first derivative and solve it for and solve it.
Mm-hmm.
If that number is positive, does that mean that it's above the graph? Does that mean that it gets a plus? Or if it's negative, it's below the graph?
Yeah, I believe that's right. Yeah.
Okay. That was my question. Because like I remember doing these, but I'm sitting here looking at it and trying to decide if it's all going to equal out. Like you're going to have 6 squared, which is 36, times by 12, which gives you a big number. Then you have -6 times 48, which is a fairly large number, but it's a negative number. And then you subtract 60 from that.
Right.
I guess I'm trying to figure out if that's going to be a positive number. So 36 times 12 minus 48 times 6 minus 60. Is it still going to remain positive? Like I obviously I can grab a calculator and do that. But
I think it will, yeah. Because -5 is that
plug in 0. We plug in 0 and then you get it equal to -60.
Yeah, -5 is that crossover point at which below that it's going to be on the negative side. And then when you start plugging in, what does it say? 1? Yeah, when you start plugging in up to 1. It's interesting, the 0.5. Oh, that's right, because you have the 60. Oh, that makes sense, because 12 plus 48 equals 60, right?
Mm-hmm.
So that makes sense that 1's a cross point. Yeah, so the positive means it's above the x-axis, and negative means it's below. Positive means it's above again. And then, so for the second derivative, I believe you use the same thing to find on that second derivative chart. So you have 24x plus 48 equals 0. X plus 2 equals 0. X equals -2. And they plugged in -3, which is going to give us a negative number. And then they're going to give us...
Passes through -2, positive, goes above.
Yeah. So once again, it's the same thing. It's above or below the axis is what we're getting from that. And that shows us an inflection point. I believe you can actually find out more information from the third derivative. but I don't think they usually deal with the third derivative that much, you know?
Oh, I've never heard them talk about third derivative yet.
Have they not? I don't know. I swear, like every time you drive it, you can pull out more information. But then again, a lot of the time, you don't really deal with anything more than a third level. What am I thinking of? Quadratic or third level polynomial anyway.
Right.
So but yeah,
So,
it
so
tells
then
you the inflection point, and then that helps you to make your pretty graph. So let me see.
so
'Cause you have
then
yeah, good.
oh sorry. I was gonna say so then for the graph down below,
Mm-hmm.
how um how did they get that? How did they get the numbers in that
All right. Well, that
to
was
graph
something that
it?
actually was very interesting to me, um, because I was actually looking. The teacher was saying that a lot of the points we don't know, but some of them we do know. Um, that we can plug in and find. It's like the points where it crosses the x-axis, you can plug in for 0. The y-axis, you can plug in.
We know the two critical points and we know the inflection point.
Right. So we know all those points, but we don't know where that curve is going to be. For instance, if you see how the dot shoots through 0, 0,
Mm-hmm.
if it actually was a little bit to the right and it crossed that y-axis at some point, we'd have more difficulty knowing where that is without plugging in 0 for x to find our y out, pretty much. Cause I don't know, the teacher was
Right.
really weird about that. She's like, well, we don't exactly know these points. I feel like you can get them. I think she was just kind of keeping it simple. Oh no, that's because the first one was just using a graph from a graph. But since we have the equation, we can find these points. If you're trying to do it from another graph, though, you can't do as much.
And you use the original equation to graph it?
Partially, yeah. So let me see. So I'm going to the top. So use the original one to tell you the domain, the x-intercepts, and the y-intercepts. That's you there?
Are you? Yeah, I'm here. Are you there?
Oh, I got you on both these things.
Hello?
Do I have you back?
Yeah, I can hear you now.
All right, my computer systems are messing with me.
Yeah, for real.
Yeah, sorry about that. Why
So
did I lose you? Oh, right, we were talking about the first derivative and those points, right?
right. So like I'm sitting here looking at the graph and at the points that were chosen.
Mhm.
It's a negative 7.9 and 0. How are you gonna figure out that you need to plug in negative 7.9? It's just kind of like a random number.
It is kind of random, isn't it? Um,
And then like the third one down is a 1.9 and a 0.
where is the? Oh, that's the. What point is that she's plugging in? Oh, that's the x-intercept, isn't it?
Mm-hmm.
Um,
Oh, I got it. I see it now.
yeah, x-intercept.
So
-6 plus or minus the square root of 36 plus 60 over 2. So you get the square root of 96, which doesn't really work well.
well, you get it says roughly negative 7.9 or roughly
1.9.
1.9.
Right. If you want the real number, it's going to be something different. It's going to be like -3 plus what's root 96 anyway? I swear I should know that one simplified. 96 divided by 3. That's me 32. So you got a 4 and 4, 8. You can pull a 4 out, but that's. I mean, you can pull 16 out, but that's about all you can pull out. It's kind of a funky one. But yeah, that's why they have such a weird number there. Sorry.
Okay. So I see this now. I see it.
Okay.
So you're gonna use for the x's. You're gonna use the 2x intercepts or the 3x intercepts that you find.
Right.
0, -7.9, and 1.9.
-7.9.
You will also. Did I lose you there?
Oh, you're good.
Okay. And then you will also use the 2 critical points that you found and point.
Right. And now I'm not positive. I think you may be able to put the critical point into the. No, you can't actually. So once you found those critical points, plug them back into your original equation. And by plugging it back into the original equation, you will find your y. Does that make sense?
Right.
Okay.
Yeah, you'll all of these, like your -7.9, your 0, your 1.9, -5, -2, and 1. I believe you plug them all back into the original equation, and that will give you the y for this graph.
That's right.
To help you plot it.
That's right, because I was thinking to myself, you could plug it into the one that it came from, but that's not true because you'll get 0. So you have to plug those into the original equation to find your actual y-axis.
Yeah.
But yeah, so now those curves, those are just kind of guessed because they're not as significant. If you wanted to, technically you can plug in every single one of them, but it's kind of hard to do that if you want to. Interesting. It's kind of making me wonder what's going to happen if you have the third derivative, though, because since you have that inflection point, technically, if you had a x to the 4th equation, you'd have 2 inflection points. I lost him again. How many times am I going to lose this guy? Anyway. You back?
Yeah, I'm back.
All right, so.
I don't know what the deal is, but.
I think last time was my fault. This one.
I think this one was my fault, and I don't know why.
Yeah, the last time I came back to the screen because I was looking at the other screen, and it was all trying to restart up again. So I'm pretty sure it was mine. Yeah. Do these make sense to you? Sorry.
Yeah, that makes a lot more sense now.
Yeah. Interesting. Do you see the analyzing graphs part 1, 2, the second equation?
Number 2, yeah.
I'm just looking. Have you looked at the graph on the bottom?
Oh wow.
It's got a very funky thing going on, doesn't it?
Mm-hmm.
So.
But in the same sense, it uses the let's see, you got 0 and 4 for your x-intercepts.
Mm-hmm.
You got 1 and 4 for your critical points, so it adds 1 to that because 4 was already used.
Mm-hmm.
Then you got 4 and 2, so it uses those.
Yeah. What's interesting though, you notice that inflection point. One of the inflection points is on top of the critical point. You notice that?
One of the inflection points is on top of the critical point.
Yeah. See how
so?
It equals 4 both times?
Yeah.
And you notice what that does to the graph. It actually makes it so it's not a min or a max anymore. Did you notice that?
Oh, right.
So it kind of throws things off because it's sort of a max, But notice if it's an inflection point, that is going to change it, and it's no longer a min or a max, but it's rather just an inflection at that point. So,
Right.
Just something to be aware of. And it looks like something's happening between 1 and 2. I don't know if you noticed that. But it looks like I don't know if it's just how she wrote it, but it almost makes it look like there's an inflection point between them, but she doesn't have one marked there.
I don't think there was. I think there's between 1 and 2. I think she was just trying to make the graph kind of curve so that it flowed and wasn't like straight lines to one another.
Yeah, probably. But it's interesting. I don't know. Has that been helpful? Is there anything you want to go through on this, or go through any of the math? Okay.
Makes a lot.
Yeah, these are actually pretty easy. If they're on the quiz, I'll probably be happy. Because I could remember most of this from memory. Just like I needed a little bit of a reminder, as you always say.
Right, I always do.
Yeah, this one, it's coming back to me. Like when I was seeing it, I'm like, oh yeah, I remember we did something weird like this, or whatever it be.
Right.
Okay.
Now, on day 3, day 3, I might need a little more help.
All right. Well, let's start hitting day 3. I haven't even touched day 3 either. Oh, we got some fun stuff going on. Okay, so I'm looking. Have you pulled up day 3 yet?
Yeah.
Okay, so you're analyzing a graph, and this one has something on the bottom. And whenever something on the bottom, you know that there's going to be something missing in your domain. In this case, you know that 0 doesn't exist in the domain. So it's all real numbers except for 0 for the first one.
Okay.
And then your x-intercepts, you solve that the same way. What's interesting is that you actually ignore the denominator.
You there?
You there?
Yep, I'm here.
All right. Sorry, I seem to keep losing you. I hope we at least have some kind of a record of this.
Well, my phone still says it's live.
Yeah, it shows live, so I figure it's live. It's just going to have tons of gaps in it.
I know. I don't know what's going on, but I see what you mean where there's no y-intercepts because is it because of the denominator?
Yes. Uh-huh. Oh, thanks. Thanks. Yeah. I believe that is right. I'm trying to think. X minus 5. Y. Yeah, it is because of the denominator affects your y-intercepts. I think.
Okay.
I think that sounds. I have a no on that, but we do know that since there's a gap at 0, it's not going to intercept y at all. It can't.
Right. So there of some sort.
Mm-hmm.
Which, I mean, you can have a vertical asymptote there, or you can have a horizontal asymptote there.
Horizontal?
Right.
You'd have a vertical asymptote there for sure. I'm trying to think. let's see. And then this thing, you can try to find out if there's a horizontal asymptote. And are you looking at the solve problem?
You take the limit of the equation
At infinity?
at infinity, yeah.
To find the horizontal asymptote.
Yes.
Which equals...
And when you divide infinity by infinity squared.
Yeah. But you use the... you use L'Hopital's rule for that. Because you'll do 5x minus 7, and that goes to 5. And then x squared goes to 2x. So then it's 5 over infinity. And then you can solve for that.
Which equals...
giving you 0.
Yeah,
right?
Which would equal 0. Yeah. So really you'd have a vertical asymptote and a horizontal asymptote at 0.
Interestingly, yeah, I think you're right. Then trying to think. So yeah, and then your vertical behavior. So your limit of 0, since you can't touch 0 anyway, at negative side is negative infinity, and on the right side is negative infinity. So your limit at 0 is infinity, negative infinity, but it doesn't actually exist at negative infinity.
Right. It's going to go down and keep going farther and farther towards negative infinity, but never touching 0. But getting close.
Bingo. So its vertical behavior is that.
What is the cross?
5x minus 6. I don't know what that one is, to be honest. I know that there can be a cross asymptote, or not cross asymptote. That's not the word I would use. But you can get a diagonal asymptote at times. But I don't think that's what the cross is. I think we might have to look at the video to kind of find out what that is.
I was just wondering if in this equation, if there was any place where your function crossed the asymptote.
It does. If we look at the graph, it shows that at 7/5 it crosses that asymptote.
Right. So that's what the cross would be. But how do you know when to use the cross and when not to is what I guess my question is.
That's a good question. I'm trying to think, how did she find the cross in the first place, actually? That's my question for you.
Well,
because look at that equation.
You set your function equal to 0.
And then you moved x squared over.
Well, you would do it just like you did to find the x-intercepts.
So times both sides by x squared. Then plus 7 to the other side divided by 5.
Are you there?
Yeah, I'm here again.
Okay.
Sheesh, what's with the internet today?
I don't know.
All right.
Is that on your end or my end?
I think that one was you, but it's been every other this whole time.
Mine said that it just said the call was ended.
Huh.
Which I was like, but that's what it's been saying every time.
I don't know then. I really don't. Because one of them was resetting on me. But this one, I was just talking to you 1 sec. Well, no, I wasn't on the right screen, though. But it doesn't show I broke. It just says that you left the group chat and then you joined up again.
That's what it said for you. It said that you left it, and then I called you, and then said you joined it back.
Weird.
I don't know. Weird.
The call dropped. We know that much.
Yeah. Anyway, no. So I'm looking here just to kind of get a feel for it on the answer sheet for the cross.
Yeah, I'm right there too.
It sets the function equal to 0, and then you solve for x. So you multiply both sides by x squared, and then you add the 7 over and divide it by 5.
Yeah. Yeah.
And then first derivative is okay. We know how to do crit points. We know how to do the first derivative chart. We know how to do second derivative points and second derivative chart.
Yeah, which is the same as the other one. So it looks like the only thing we really have to focus on this one that's different than the first one is going to be we have to worry about the cross, horizontal, vertical behavior, and our asymptotes are the only real things we really add to it.
Yeah, but like in your first derivative chart,
yeah,
or like when you're finding the derivative, you found the derivative, and then you find the crit points where you set it equal to 0.
right.
We know that it cannot equal 0. All right.
Right.
So that ends up on the first derivative chart, and I like how you put like a little asterisk above it to say, hey, this doesn't equal anything. But it's funny that I'm like looking at this that those are still on the first derivative chart, because I think I would have not put it on there because of whatever reason. But I guess like on the first derivative chart, it is necessary because it shows that inflection from negative to positive.
Right. And in a way, it kind of is a minimum. I mean, a really odd one, but the limit does go towards a minimum point. It has a limit there. It's just that it doesn't actually exist. It would, I mean, in a way, that's actually really nice because if you hadn't realized beforehand that it was going down to negative infinity, taking the derivative and solving for it would immediately tell you, oh, this is going to go somewhere.
Right.
But yeah, I was kind of thinking of the last one we were doing. It's kind of similar that it seems like the first derivative chart can be affected in different ways. Like in the second one, because there was an inflection point at 4 and the derivative is at 4, it changed how that first derivative chart actually worked. And it seems like that same thing happens with this one. If there's a asymptote or stuff like that, that can screw with our first derivative chart and mess things up.
Yeah. That's what it's looking like.
That's something to take into consideration. It looks like what's also interesting is it's also an inflection point at 0, isn't it? Or am I wrong? No, there's no inflection point. She's making a mark of it anyway, though. I don't know why, though.
Right. Well, that's my question. Like,
I don't know what's going on there. What would happen if you take the fourth derivative, huh? You get something else fun, wouldn't you? You'd get you just get
well, your denominator is going to keep growing an exponent.
Your top one's going to keep shrinking.
I
think maybe.
Now it grows too.
Okay. Yeah, there's some mad stuff. Oh wait, no, that's funny. It never changes. Look at that. So if you look at the original, there's one x, and then in the second one, there's still one x. In the third one, there's still one x, but that denominator keeps getting bigger and bigger every time.
Yeah, and then your numbers on the numerator keep getting bigger, but there's still only one x.
Yeah, I'm guessing then if you were to take the third derivative, the same would probably follow, that you have one x, and then you'd have a fifth derivative on the bottom as well. That's interesting to note. I'm sure there's something that we can learn from all those points, but this is all they really want us to learn right now.
Right.
And going to that second one, I don't know if you want to take a look at that one, but I find the second one just as interesting, where it has 2 horizontal asymptotes.
Oh, wow.
As you see, it's approaching 1 and -1. This is what's this?
But that you have 2 horizontal asymptotes because of the square root in the denominator?
I think so. But I think it's, oh, crud. What am I thinking? Something like that. So it's x over x squared, the square root of x squared. Doesn't this look like a arctan or something like that to you? Or arcsine or not, or like one of those things? X over x squared plus 2.
Something like
Doesn't it look familiar somehow?
x over x squared
Or hyperbolic?
plus 2. It's inverse tangent.
Inverse tangent? Yeah, that sounds right. Because if you look at it, it's a tangent on its side.
Yeah, it's an inverse tangent.
Gotcha. Is it a negative number? It's not negative. Maybe it's supposed to be negative, but yeah, you can see how it's been. Oh, I got it. It's a tangent that has been flipped over the axis of y equals x. Does that make any sense?
Tangent that has been flipped over
The line
the axis,
y equals
the
x.
line of x. That doesn't make sense.
So imagine there's a line going at y equals x, or where y equals x. So it's where you go up 1 and right 1 every time. Just a diagonal bottom left to bottom right line.
Oh, okay. Yep, I see it now.
So if you flip it across that axis, that's how you get this.
But how do you know that you need to flip it across that axis? Because it doesn't show an asymptote there.
Doesn't show an asymptote. No, it doesn't. Well, it's not truly an asymptote. It's a, what do you call that even? I forget what you call it, but I know how to recognize it. Good.
Right, and I mean, I'm just looking here at on the critical points, or like when you find the first derivative.
Right.
And then you move the part with the exponent, with the negative exponent, to the denominator. You have like 2 over x squared plus 2. You there?
There we go.
All right.
Okay, well, we'll get this
one
done.
One way or another, we're going to get this done. What's that?
Sorry, what'd you say?
I said one way or another, we're going to get this done.
Yeah, I was thinking the same thing. We'll finish this page and then we made due diligence on it.
Yeah, for reals. No, I was just noticing on the crit points, where it has 2 divided by x squared plus 2 to the 3/2. Well, that.
Oh, sorry, just a second. I'm on the wrong page. Yeah, 2 over x squared plus 2 to the 3/2. Yeah.
Right. So the inverse tangent function, like the derivative of an inverse tangent, is 1 over x squared plus a squared.
Was one
Is that
over a squared?
1 over x squared plus a squared.
Right, and in this case, our a squared is 2, right?
Right, but you can't. I'm thinking the more I'm looking at it, I don't think it can be an inverse tangent function.
You don't think so?
No, well, for one, it's to a power, and 2, the a squared part. It would be hard to have a by itself at some point because you don't know what the square root of 2 is.
Yeah, it still could exist. It just would be messy.
I mean, yeah, I mean it could. I'm just wondering how to know that the graph is shaped this way.
Yeah, I'm trying to think of the same thing. Because if you're noticing on this one, we really don't see much what's going on here. I mean, she only has 1 point at 0, 0, and then an asymptote and an asymptote. You can clearly see, though, there are inflection points. And she does mention
Right. Well,
but she doesn't put it on.
uh-huh.
Because there's an inflection at +1 and -1 where it's starting to go up, and then it inflects and starts going straight to the right towards that. I don't know what you call that, though, because it's flexing, but it's not flexing like it normally does. You know?
Right. Well, like if you look at the inflection points, it suggests that at -1 the graph is above the x-axis,
Yeah.
and at +1 it's below the x-axis.
Which is actually completely wrong, isn't it?
And if you look at the first derivative chart,
Uh-huh.
it would suggest that everything is above the x-axis.
That's interesting. Oh,
So,
however, that is for the graph of the derivative, not for the graph of the original equation.
right. And it is for the graph of the second derivative, but not for the graph of the original equation.
Right. That's kind of part of the thing why it's plus 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 or plus negative. Because it's not true for the original. I was totally getting thrown off for a second there too. I think that's why it's positive, 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 and positive, negative, because it's not actually for the graph we're working on.
Yeah, right.
But I hear what you're saying, though, because you want to know why it's making that very peculiar curve and how to tell how deep that curve is and whatnot, right?
Yeah.
Um,
When obviously, like, you can see that there's horizontal asymptotes at 1 and -1, so you can't go
anywhere,
past those.
right?
And so if you know that on the right side of the y-axis it's positive, and on the left side it's negative, you can draw something in there and make it come up to the asymptotes and run along the asymptotes.
Right, and you can also check to see if it's getting closer to them or not. But I mean, generally speaking, they are getting closer to that point. They're not going to bounce around in there. I mean, that would be a very annoying equation. I mean, just imagine a little sine graph on the top and a sine graph on the bottom going up and down in between 1 and 0. I mean, technically,
that would be awful.
I don't even know how you'd mess with that equation or how you'd get it. I'm sure there's one that exists, but oh well. I actually have seen some really crazy ones where they, anyway, but they're, yeah. Fortunately, for the most part, it's not. And since there's no sign in there, we know there's no ovulation or it's not bouncing up and down. It's going to go in one direction unless it has an inflection point or a max and min. But we know there's no maxes and mins. If it was jumping up and down, it would have maxes and mins, and we would know that, even if it was a sine. Because in the sine, you find your maxes and mins, it's going to give you a series of numbers, right?
Yeah.
It's like every pi half or something like that, you get a max or a min, right?
Right.
So even those, you get that answer.
Yeah, as it oscillates each direction, you know.
Oscillate. There's the word I was looking for. I don't know where I was pulling ovulate out.
Yeah.
But okay. Oh, great.
This makes more sense now that I'm like talking it through.
Good. I'm glad to hear it.
Is there anything else you need help on?
I think this week you're doing pretty good. This one's a pretty straightforward one. It works for me. I mean, I wish I knew how to make those curves look the way they look, but beyond that, and I don't think the teacher really teaches you that. It's just mostly, hey, here's points, and you're gonna have to intuit the rest of it.
Right.
So, but no, I think that'll work, and it's getting a little late, so probably should let you go. And you're staring at your eyeball, it looks like. So, oh, you look tired. I can see those bags.
I've always had bags under my eyes.
Well, good week's sleep and see them go away.
No, I was born with them.
Possible.
Genetic, I'm sure.
All right.
But anyway, sounds good.
All right. Well, I'll let you go. Hopefully this thing all worked, huh? I'd be very mad if we lost all of our
Hopefully
data.
so. Yeah. Well, we'll submit what we have, I guess.
Fair
It'll prove that we were both here.
Right. Okay. All
So,
right.
anyway, just send me the link.
Okay, we'll do.
All right. Sounds good. Thanks.
Yeah. See ya.
Bye.